Hey, this is ECE 4430, project number 1. In this project, we're going to characterize some MOSFETs using cadence tools and curve fitting some experimental data. I'm Joshua Roper.
And I'm Project1 Zhu. So firstly, we did the N MOSFET models. So in order to get our model fit our experimental data, we need to get our EKV model working. And in order to get the EKV parameters, we need to extract a series table of values according to our given data. So the table is shown here, and in this gate sweep scenario, we extracted our threshold voltage, threshold current, and kappa value based on the data. So basically, in the below threshold curve fit, we get our kappa based on the slope, and then on the above threshold curve fits, we get our V threshold voltage and threshold current. So once we have our EKV parameters, we use the schematic here to do the gate sweep, and then we tweak some our parameters to fit the original data. And noticeably, we mainly tweak the KP values. We raise it by a factor of approximately a factor of 10, and then the current will fit well with the original data. And then for the source sweep, we get our table of parameters like the above threshold kappa based on the above threshold curve fits, and then we get our K based on our below threshold curve fits. And again, we use our parameters and to plug into the schematic and do the source sweep. This time, since the model isn't changing, so similarly with our gate sweep data, we have some offset in the below threshold region. This is probably because our threshold voltage isn't low enough, because we are extracting our threshold voltage based on above threshold curve fits. So maybe if we implement our threshold voltage with below threshold voltage, below threshold curve fits, then maybe the curve fit will fit more. And then for the drain sweep, here we mainly focusing on channel length modulation, and we do a curve fit on the saturation region here to get the early voltage, and then we convert the early voltage into lambda, which is 1 over early voltage, and then we plug it into the EKV model. And again, we use the schematic here to do the drain sweep, and the experimental data and the given data fits quite well, and the slope is also fitting quite well. And so yeah, and and for the gate voltage, we choose the gate voltage to be 285 millivolts, which is slightly above threshold, as you can see on the plot.
Okay, so for PFET, it's a really similar way we did this. So we curve fit the above threshold and below threshold regions to get VTO, ITH, and kappa. And from that, we started building our EKV model. And so again, mostly for this, we changed our KP value to get the simulation to match closely with the experimental data. And for the source sweep, again, we curve fit below and above threshold to get our kappa values and our K values. And so again, we have our EKV model, which fits pretty closely. And then for the drain sweep, we got our saturation and ohmic regions, and we curve fit our saturation region to get our lambda parameter. And so we just plugged this in, and it was very close for the curve fit for the stimulation. And notice again, our gate voltage that we used here was 1.2375 volts, which is really close to the above. It's just slightly above threshold. So
yeah, and then we want to experiment about the effect on changing the width and length, and see what the curves will vary for the gate sweep. So firstly we do the infet. So we have 3 sets of data, one with small width and one with small length and one with small width and length, and the data is shown below here. And so first we did the schematic, and then we do the layout based on the schematic. So as you can see, we have the NMOS device, and we have a bulk which serves as a body and body terminal, and we have a contact here to serve as a gate terminal, and and we verify it to pass the DRC and the LVS rules, and then we extract we extract the layout and do the simulation. And as you can see here, since we have 3 data set and the W/L ratio is changing, so as the W/L ratio is increasing, the current will pop up. So this is because the K parameters is directly proportional to the width and length ratio. So similarly with the PFET, we do our 3 sets of layout, and one with small width, one with small length, and one with small width and length. And so we extract our layout to do the simulation here, and as you can see, as we increase the ratio, the current will pop up.
And again, you can just pause the video to see what equations we used to do for our curve fit. Thank you for listening.
Thank you.